Hi, everybody. It's a pleasure today to present Guilherme Silva. Guilherme Silva had his PhD at the University of Leuven in Belgium in 2016. Then he had a long PhD in Michigan, University of Michigan, as assistant professor, postdoctoral assistant professor at Michigan from 2016 until 19. And he is now, as a young researcher of FAPESP, working currently at the ICMC of the University of São Paulo. And so it's a great pleasure to receive you, Guilherme. Thank you very much to accept the invitation. And today you will speak to us about random matrices. So please, thank you very much.
Thanks a lot, Sandro, and thanks, Michelle, for also inviting me here. It's nice to speak to you, especially our colleagues from UFSCar, just like a few miles away, even a mile away. But well, unfortunately, we don't see each other in person now. But it's good to see some known faces here online. Okay, I almost forgot that I have to actually share my presentation, of course. Yeah, so it's coming through. I hope you can see it now. Yeah, so today I'm going to be talking about random matrices, and also actually I'm trying to make a connection or making a connection with certain random growth processes. But before going into that, let me go back to the basics so that at least I can entertain you for a few minutes with things that most of you may know about. So I want to start with something very simple. So let's just start with some IID random variables, find means and variance, or put any good condition as you like on those. And of course, as we do in one of the first things that we see in undergrad, we start out taking SAMs of random variables, right? So I'm just noting them by SN. And we see that already in undergrad, the central limit theorem. What does it say? It says that if you look at a sum of random variable, but not exactly the sum, but you recenter it. So you subtract from it its mean and divide by the variance, or the standard deviation, variance, the root of variance. Then and you look at the fluctuations of this quantity. And so basically, those are the fluctuations. And you see that those fluctuations, they converge to a Gaussian random variable. Right? In other words, rescaled sums converge in distribution to a Gaussian random variable. Right? And this is, of course, very common to many of you, very familiar to many of you. But I want to stress a few things here. The first thing is that perhaps the first or one of the first versions of the central limit theorem appeared in the early 19th century, which is like known as the Moivre-Laplace central limit theorem, which was proven for Bernoulli random variables. So random variables with only taking like two possible values. And of course, for those random variables, everything is very explicit. You do calculations and you prove it basically using calculus because everything is very explicit. But perhaps like the most or among the most general versions that we know of are the Lindeberg-Levy version of central limit theorem for more general random variables, of course, always under some conditions. But this was proven like almost about a century later, just at the starting of the 20th century. Right? So it took about 100 years for people to go from explicit calculations to a more conceptual proof of the central limit theorem. And I want to make a parallel with that later on. But the other thing is also that I want to stress here. So like in physical terms, what you're saying is that, okay, you look at sum of random variables, and the sum of random variables, what you're saying is that it evolves more or less according to the mean of the sum, which in terms of number of terms, so if you look just at the number of terms in the sum, this is of order n. Right? So I want to stress here the n. Right? The mu here is just a constant, constant, but what we really want to stress that the sum of random variables is of order approximately n. but it's not exactly n. It's approximately n, and you have certain error, the fluctuations, and you are fluctuating with order root of n. Right? So you have a quantity of order approximately n, but you could be above or below it a bit by order root of n. Or in other words, I put correlation, but that's not what I mean. I mean fluctuations. So fluctuations are of order root of n. We're gonna not use it, but also make a parallel with that later. Okay, and I am a mathematician talking probably with many statisticians, and but if you, okay, before even going there, but let me just like stress that of course we can state the central limit theorem just saying like in very let's say lazy words, just say that the Gaussian distribution is the universal fluctuation law for sum of independent random variables. You take independent random variables, you look at the fluctuations, and doesn't matter what random variables you started with, you always end up with a Gaussian. And that's what the word universal means. Doesn't matter the distribution of the individual variables. At some point, you're going to see Gaussian fluctuations. So the fluctuations are universal. They do not depend on the distribution you started with. And yes, as a mathematician talking to statisticians, I want to scare you, but just a tiny bit, and I give a proof of this central limit theorem, a one-line proof. So of course, hand waving a lot for a reason, right? So some people say that every math talk should contain a proof, and that's going to be my only proof in this talk, and it's going to be a one-line proof for a reason. So, of course, there's several proofs of central limit theorem. The one I find, okay, I know just few, certainly there are many more than I know of. The one that I find more sort of clean is the one that goes through looking at the moment generating function, right? So basically what we learned is that, okay, looking at the distribution of the random variables is nice, but perhaps not so easy. So instead of looking at that, let's look at the moment generating function, or what we call Laplace transform in mathematics, right? So we do that. So let me do it. So you start with the moment generating function for the sum, and this moment generating function, here is basically just the definition of it, right? It's a function of a variable t when you take expectation of e of minus t times the sum. Right? But here's where the magic happens when you have independence. Right? So because you're doing expectation of products, this splits into products of expectations. All the random variables have the same distribution. So the moment generating function becomes just a power of the moment generating function of one single variable. So the magic just happened to you. You don't need to look at sums. You look only at one single variable, and that's because you look at the moment generating function instead of looking at the distribution of the sum itself, right? And then you do just calculus, and the calculus is going to tell you that when n goes to infinity, and it's literally just calculus, when n goes to infinity, you recognize this expectation, this moment generating function to the power n, you just recognize it to be the exponential function when n goes to infinity. And you just compare, and then you look at the table, and you see that the exponential function that you get at the end coincides with the moment generating function of Gaussian. So in the limit, the moment generating functions coincide. You do a little bit more work to recover the convergence in distribution from this convergence of the moment generating functions, right? But everything in terms of calculations really happening is just calculus, right? So there's not much there. But I want to stress this fact that you don't work back with distributions, but you work with the moment generating functions. I'm going to make a parallel later as well. And of course, here the key point as well is that you were dealing with independent random variables. So you could split the moment generating function of the sum just as a product of moment generating functions, and then turning that into a power, right? Independence was key here. But today I want to talk about, let's say, moment generating function-like transformations or Laplace-like transformations towards the end. But I also want to talk about universal laws that arise by looking at those quantities. But those universal laws, so they will be taking place for correlated systems. Here we are talking about Gaussian's universal law that we see to arise as through the moment generating function for independent random variables. Now we're going to put correlations into the game. Right? And we're going to look at several different models here. I'll try to be as much focused on ideas as possible rather than on calculations itself. The first quantity that I want to look at, or the first model that I want to look at, is random matrices, as the title suggests, for historical reasons, as I'm going to explain. And one of the first people to consider random matrices like in a serious manner, actually, it was Dyson back in the 50s and 60s. He was probably not the first one, was the second one, but the first one I'm going to tell in just a moment. And what was the idea of Dyson? Dyson was a physicist. Some people say that he should have earned a Nobel Prize, but he never did. Anyway, but Dyson was looking at what they call heavy nuclei in high energy physics. So think about some compound. Right? And what he was studying was the reaction of those nuclei under some excitation. So, okay, so you have a nuclei, you excite it, you shoot some light, or you put heat on it, and this nuclei is going to start to react, and it's going to scatter some quantity, it's going to scatter some energy there. And you start measuring this energy, right? Or this light that's reflected. And okay, I don't know much about physics, but that's, let's say, with some it's like pictorial example of what happens. But at the end, what you do get is a figure like this, and this is extracted from a book on random matrices. So this figure is from a measurement experiment along the lines of what I just described. They scatter some light, they shoot some light into some heavy nuclei, and this nuclei it just like scatter some energy levels, scatter some light, and you get a picture like this, which is the energy that is reflected. And here in the top picture is for, I guess they call it thorium 232. And here in the bottom picture is uranium. And okay, there's a whole interpretation in physics about those pictures. I don't know about it. What I do know is that they were interested in those peaks. So you see that both on the top picture and on the bottom picture, there's some peaks here that emerge, right? And those peaks have interest in physics. They describe the energy levels of your system. And Dyson was looking at it and saying, okay, it may be hard to really mathematically describe those energy levels, those peaks for a given nucleus, but I may try to describe the picture or the statistical properties not when I look at one specific compound, but when I look at several of them several times, I may perhaps be able to describe some common statistical features in those energy levels. Okay, what physics was telling him is that, okay, to describe that mathematically, you have to look at the corresponding Hamiltonian for the system and compute the spectrum of this Hamiltonian. The spectrum of the Hamiltonian will correspond to those energy levels, or the eigenvalues of this Hamiltonian will correspond to those peaks. I don't know how to describe that exactly. I don't, at that point, they didn't even have like computer resources for that, but okay, let me try to describe that statistically. What does it mean? It means that my Hamiltonian, whatever it is, should be random. So, okay, I'll look at the spectrum, which is also random, but okay, Hamiltonian is infinitely dimensional. Let me approximate it by something of finite dimension. So let me look at a matrix of finite dimension. Hamiltonian random, matrix then is random. And then let me look then at the eigenvalues of this matrix and see if the eigenvalues of this matrix have something to do with this picture that I'm seeing here when I do my experiments. And that was Dyson's ambition. And we can actually compare that nowadays with computer. My computer can do that for me. And here's just like a little, little picture, or two little pictures here. What I did, I sampled here on the top, here on this top line in red, I sampled a random matrix of size 20, a Gaussian matrix. I'll tell what that is in a moment, but I sampled it with my computer, 20 by 20, so I have 20 eigenvalues here, and they happen to lie in the interval minus 6, 6. Right? And then what I also did is that I just sampled 20 points in the interval minus 6, 6, uniformly and independently. According to Dyson's envision, the eigenvalues here, the red dots, should be a good description of the statistical features of those pictures. Well, of course, I would have to go through a more solid statistical study to see if this is really true. But we can see already with our bare eyes that at least like in those pictures, the eigenvalues here, the red dots, they correspond to a much better fit than the uniform points, uniform independent points. Why is that? One common feature that I want to stress to you, and which is very important in random particle systems in general, especially in random matrix theory, is that the points here, they're not exactly equally spaced, but you don't see cluster of points. You don't see many points all together, and you don't see also gaps, huge intervals without any eigenvalues. So there's more or less a equally well-balanced spacing between the points here, between the eigenvalues, which is not what happens with the uniform points. So in a certain sense, the uniform points are not uniformly distributed here in the sense of what we see, right? You see huge gaps here, and you see also clusters, several points lying in the same interval. But that's actually to be expected, because if I put a point in one, let's say if I sample a point and I happen to get very close, let's say to -4, well, my next point doesn't know anything about the previous point. So it still has chance of being close to -4. In eigenvalues, they will be correlated. So they know more or less better the position of nearby points. So they don't like to be very close to one another. They don't like to be very much spread. So then you get those pictures more well-balanced, so to say, in terms of distances between consecutive points. And if you look at those peaks, this feature is more or less also present. You see the peaks here, they don't tend to be, okay, you may have one or other very close, but you don't see like several peaks altogether. And you also don't see large gaps between two consecutive peaks. So in that sense, already with bare eyes, we see that those points are a better candidate for fitting into those peaks than really the uniform points sampled independently. Right? And this Dyson was already like explaining to us back in the 50s and 60s. Okay. Well, of course, I was talking about a GUE matrix, and what I have to do is I have to tell you what that really is. So very quickly, let me tell you what a Gaussian matrix is. And this is going to be one of the central objects that we're going to be looking at. So what I'm doing here, okay, I'm taking normal random variables, MJJ, MJK, I, and R. I'm normalizing them in a certain way. Don't care much about normalization, but I'm taking normal center at the origin with certain variances here, or certain standard deviations here. Right. And why am I doing what I'm doing? So those are all real random variables, and then I'm placing them. Okay, some of them along the diagonal of a matrix of size n, square matrix of size n, and some of them I'm placing, let's say, on the top upper right corner of the matrix, and I'm placing them here so that I have a complex number. So the real part of this complex number is a Gaussian. The imaginary part is also a Gaussian, right? So this is a complex number with real imaginary parts Gaussian. Or if you prefer, this is a complex Gaussian number. Anyway, and then I'm doing here that I'm making the Hermitian version of it. So whatever I place here on the upper part, I just put its conjugate on the lower part, right? Just to have some symmetry, just to construct an Hermitian matrix. Okay? And because I want to have the symmetry, the diagonal then is just real, right? And all those entries, as I said, they are Gaussians, appropriately normalized. In particular, the variance has to do with the size of the matrix. Just because I chose to. So that I normalize it here, so I don't need to normalize in the future. That's it. That's why I place here this 1/√n here, and 1/√2n here. Okay, so this is what is a Gaussian a Gaussian matrix or GUE matrix, which stands for Gaussian Unitary Ensemble. Ensemble here is just the word for and Sandro may correct me if I'm wrong, but ensemble here is just the word for collection, basically, or model. Right? And okay, but there's the word unitary. Why unitary? My matrix Hermitian. Why I call it Gaussian unitary matrix? It's just because this distribution, so here I'm defining basically a random matrix. It has an underlying distribution, of course, and this underlying distribution is invariant under rotations, invariant under unitary conjugation. So this unitary does it just an expression of this invariance under rotations, which is similar to Gaussian vectors. Right? Gaussian vectors also are invariant under rotations, and that here is just the same. And of course, statisticians like that, they're symmetric matrices, so matrices with real entries. I could have done like real matrices here, but it turns out that they're much more complicated to analyze. I want to show you one or all the results here, and they're just like a tiny bit more complicated to state as well. Sort of a choice I had to make. Gaussian, the complex versions are a little bit easier to work with, but everything I'm going to tell you about, there is a version also for symmetric matrices. So the same construction, but with real random variables, no imaginary parts here. Okay, but what do we know about those matrices? Well, it's an Hermitian matrix, so it's diagonalizable. It has certain eigenvalues. So it can now be diagonalized by unitary matrices, and those are the eigenvalues are the objects that we really like. For several reasons. One of them is because, okay, once you diagonalize, you're going to see that this U, the matrix that diagonalizes M, it's just uniformly distributed over unitary matrices. So that's easy to handle, not for today. I just want to look at the eigenvalues, right? Well, my matrix is random, eigenvalues are also random. Right? So Gaussian matrix eigenvalues are not necessarily Gaussian, because in the process of computing eigenvalues, I'm doing very nonlinear things there. Remember that I need to compute some zeros of a polynomial and this polynomial has certain coefficients written in terms of determinants, so in the terms of determinants on the entries of the matrix, so very nonlinear. And so eigenvalues, there's no chance there, or at least like there's no hope that they're going to be independent. They're not. But how do they look like? And here what I did is I sample a matrix, I guess it's of size 50, if I'm not mistaken. And I made an histogram of the eigenvalues here. And what I'm going to do is that I'm going to start increasing the size of the matrix, and I'm going to see what happens with the histogram of eigenvalues. So those are the eigenvalues, right? So I'm saying here in this interval, there's like 2 or 1 eigenvalue. In this interval, there are 2 eigenvalues. In this interval, there are 3. I'm going to start increasing my matrix and see what happens with the histogram. And you see that quickly enough, the histogram starts to sort of not shake too much anymore and starts to create a shape. And this is basically the law of large numbers for the eigenvalues. If you place that in a mathematical statement, it's what they call the semicircle law. You take the eigenvalues of a random matrix, you make a certain average evaluated at any function, any weighted average, and this weighted average converges as the size of the matrix grows. It converges to this integral of your so to say test function of your statistics, converges to the expectation of your statistics with respect to this circular law, this distribution root of 4 minus x squared, normalized, of course, which is nothing but the graph of this semicircle here. So what we're seeing here is just that the histogram indeed converges to a semicircle, right? To a half circle, if you prefer. And this is called semicircle law. And as I said, that's basically the law of large numbers for the eigenvalues. That's how they behave. And globally, I'm looking at all the eigenvalues. So I'm making here some statistics of all the eigenvalues all together. Of course, I could look at several quantities at the same time, so looking at global statistics that we call, or I could look also at other types of statistics. For instance, I could look at extremal statistics. For instance, I could look at the maximum eigenvalue, the eigenvalue which is like the largest of all. By the semicircle law, if you just look at a semicircle law, all the eigenvalues are going to the semicircle. In particular, they are accumulating the interval minus 2, 2, which means that the maximal eigenvalue is converging to 2. That's just an immediate consequence. Okay, as I read, if you want to say so, a law of large numbers for the largest eigenvalue. Okay, but once I have a law of large numbers, I can start asking about fluctuations. And remember, that's exactly what we did with the central limit theorem. We look at fluctuations, they converge to a Gaussian. And there's also a central limit theorem for the largest eigenvalue here. And here's how it goes. Well, what is this? So this is the probability that all the eigenvalues are at most 2 plus an error, right? Placing all the eigenvalues to be at most 2 is the same as saying that the maximal eigenvalue is at most 2, right? Because the maximum controls all of that, right? And now, but let's look at this error, this tiny error that we're making. This is just like the variable of the fluctuations, right? So you prefer to look at central limit theorem in the usual way. You just put those lambdas minus 2 divided by whatever this number here is. And what the statement is saying is that the fluctuations of the maximal eigenvalue converge to what we call the Tracy-Widom distribution. No longer a Gaussian, you don't have Gaussian fluctuations, but you have now what we call the Tracy-Widom distribution that's going to follow us quite a bit in this talk.
Guilherme, sorry,
yes.
what I didn't understand, what is this inequality? So lambda 1 up to lambda n is smaller or equal to 2. What do you mean? It's a function of them? What is it? A rescaling?
No, I mean all of them. I'm asking the probability that all of them, all the eigenvalues
all of them are
at
smaller or
most
equal to that. Okay.
Yeah.
Okay.
So I could have placed the lambda max. I don't know why I didn't do it. But no, it's basically because if you ask that all of them are at most 2, you're also saying, okay, the maximum of them be at most 2. Right? That's what my sloppiness is doing. Yeah. So I'm just asking for that probability, right? So I'm looking at fluctuation of the largest eigenvalue, right? And those are given by the Tracy-Widom distribution, and I'm going to tell you what that is, right? And here's a picture. Actually, this is I have to thank my master student Carla, because she did this picture for me. I always had a picture of the Tracy-Widom distribution, but she was brave enough to also do that, like sampling lots of random matrices. And I guess here's an histogram, if I remember correctly, of matrices of size 200 sampled 1,000 times, if I'm not mistaken. Then you get this histogram. Anyway, yeah, so this is the Tracy-Widom distribution with an histogram. Okay, perhaps doesn't tell you much. It's more or less like the Gaussian, but not quite. So if you look at, here's an histogram also with a Gaussian. In red is the Tracy-Widom distribution, and in blue is a Gaussian. And what I did is that I just chose a Gaussian with the same mean and the same variance as the Tracy-Widom. Right? So this is skewed to the left. And actually, they look very much alike, but they are not. Probably it's like a lot that they're different. For instance, if you look at the trace, and the Gaussian here has tails like exponential minus x squared. The Tracy-Widom will have tails of order e of minus x 3/2, if I remember correctly. So the tails are a little bit weaker. But here they have like stronger tails. The Gaussian is e of minus x squared, and the Tracy-Widom is e of minus absolute value of x to the power 3, if I remember correctly, with some constant different. So although they may look the same, they're not quite the same, right? Of course, those are just graphs. What do I mean by that, right? But there's a rule to describe the Tracy-Widom distribution. Well, for Gaussian, we have a formula which is pretty easy to handle. Here it's much more complicated, and this formula is through differential equations. Don't care much about the formula, but it's just saying that to get your Tracy-Widom distribution, you have to solve like an ODE with appropriate boundary conditions. That's what it's saying. This ODE is known as a Pain-Levé equation. A little bit more complicated, no explicit formulas. Okay, it is what it is, right? But I want to highlight here is that this Tracy-Widom distribution goes through not only for Gaussian matrices with Gaussian entries, Gaussian dependent entries, but actually goes way beyond matrices with Gaussian entries. You could even have matrices with correlated entries, and you still get Tracy-Widom distribution. So here comes universality. The Tracy-Widom distribution is the limiting fluctuation field for a large class of of distributions, random matrix distributions. So no, not only Gaussian, and not only matrices with independent entries. You could have also correlated entries and still get the same trace-Williams distribution as the limiting fluctuation distribution for the largest eigenvalue. So it's really universal. Okay, as I said, I want to talk about some growth processes. I hope I managed to do that in the next 20 minutes. I'm going to talk at least about two. Let's see if I manage to get the time to talk about three. And those are very simple, and they're going to relate also to this to the trace-Williams distribution. The first one I'm going to talk about is about random permutations. So it's a very simple problem which has a very nice history that I'm going to mention in just a minute. Let's look at the problem itself directly. So suppose I start with a permutation of size n. Here I chose a permutation of size 7 to simplify my life. Right, so I'm sending 1 to 2, 2 to 1, 3 to 4, 4 to 5, 5 to 7, so on and so forth. I don't want to look at the permutation itself, but I want to look at increasing subsequences. So for instance, when I look here in the bottom row, the numbers 2, 4, and 6, they come in increasing order, obviously. So I'm just going to separate that as a possible increasing subsequence of my permutation. Right? And in particular, I want to look at the length. And the length here is just 3. Right? I have 3 numbers in this increasing subsequence of my permutation. Okay, I have several other increasing subsequences. For instance, this other one, 2, 4, 5, 7. This is also an increasing subsequence. And this is a bit bigger, has length 4. Start doing the math there. There are going to be lots of increasing subsequences over there, different lengths as well. And let me denote by Ln of sigma the length of the longest increasing subsequence of a given permutation. So in this example, the permutations of size 4. The permutation of size 7, but the length of its longest increasing subsequence is of size 4 here, right? Which comes from this one, perhaps from more subsequences as well. Anyway, so go over your permutation, all possible increasing subsequences, you pick the one with largest length. You just encode, you keep track of the length. Now, okay, we're doing here probability. Let's then make the permutations random. You just make them uniformly random. You have n factorial permutations, so you put like a distribution there, which is uniform. So probability of a specific permutation is just 1 over n factorial. And then you ask the simple question, okay, what's the length of the longest increasing subsequence of a permutation, of a random permutation? This is the problem that Ulam asked in the 50s, 60s, which is basically what you can say about the length of the longest increasing subsequence of a random permutation. Okay, can you even compute the order? I mean, how exactly does it grow? And this actually sparked a lot of actually nice developments. The first one to look at that carefully were Shikhin-Kerov and Logan and Sheep, and that's independently, but almost at the same time, they proved essentially the law of large numbers for this longest increasing, the length of the longest increasing subsequence. They proved that this length grows with order root of n, and it goes to 2 root of n, right? So the expected value is approximately 2 root of n, right? And this was for, this is when n goes to infinity, right? Okay, once you have law of large numbers, so you're saying basically here that the expected value is approximately 2 root n. Next question is, okay, I have law of large numbers. What can I say about central limit theorem, fluctuations here? What's the order of the fluctuations? What sort of limiting fluctuation distribution I have? And it took, okay, you say 20 years, about 20 years for this to be proven, but it's quite a nice story because people didn't even know what the sort of the order would be, what the order of the variance would be for this problem here, for the length of the longest increasing subsequence. And it came as a big surprise for the community when Beikdati and Johansson in '98 proved the central limit theorem for this longest increasing subsequence. First off, it was not obvious that fluctuations would be of order n to the power 1 over 6, remembering that the n here is the length of the permutation, which is random. And second, they proved that the limiting distribution for the fluctuations is precisely the Tracy-Widom distribution. And that was the first time that this Tracy-Widom distribution appeared outside the realm of random matrix theory. So it was quite shocking, so to say, for the community. But it turned out that from this moment on, many people start investigating other models and start to find this limiting distribution all over the place. Right? And okay. So perhaps, yeah, as I said, so this is the same distribution as in random matrix theory. What do random permutations have to do with random matrices? Right? Apparently, they have a lot in common. Right? I'm going to give a more detailed account of this of the history around that problem, or around this evolution of development of results surrounding this Tracy-Widom distribution. But let me talk about one final model here, which is like a totally asymmetric simple exclusion process, which quickly turns into a random growth model. The model itself consists of particles that I'm placing here on the negative axis and a certain shape here, which is just like a corner, downwards corner. So this is the model. I'm going to place some dynamics here. But I don't like particles. I rather place the cars there. So I'm going to do it with cars so that we remember that this can be seen as a model of traffic, of car traffic. And how is this model? Imagine during a traffic and they're waiting for a turn to move forward, right? So we're going to model that by clocks, by random clocks or random alarms. Those alarms are going to ring at random times, right? Each car has its own alarm, and the alarms are independent and ring at random times. Okay, so let's say that the first clock rings. When the first clock rings, the car looks forward and sees if it can move. Okay, in this case, there's nothing in the front, so the car moves one step forward. And I wanna look at the traffic jam, the traffic flow here. I wanna see how many cars move through this point. So I'm gonna encode that into this shape here, this V shape. I start with a V shape graph, and what I'm gonna do now is that whenever a car stops on a downwards corner, I turn the downwards corner into an upwards corner, this way. And I keep running my model. Oh, another clock rings, the corresponding car tries to move, but in this case, the car is blocked by a car in the front of it. So then it doesn't move, stays put, and then I keep running my time here, clocks ring. When the clock rings, the car sees if it can move, and if it moves, the downwards corner moves to an upwards corner. And you keep doing that forever and ever, and then you see that you have on one hand like some particles jumping or moving here on the integers, and on the other hand you see this graph that's evolving upwards. So it's a growth process that's emerging. And over there we had 4 cars. Here I have 180 cars. They are represented by red dots here on the negative integers. And I have here the cars, the shape here in blue. So I run the dynamics, and what you see is that the shape starts to grow, which is in blue, and the shape is all erratic, right? Sort of a little bit chaos there. It's wiggling a lot. And in green, what you see, so this shape is random, it's wiggling a lot, it's random. Well, what you see in green, there is essentially its expected value. So it's sort of the law of large numbers. For blue, is exactly the graph in green, right? Yeah, okay, and what is, and what's important for us here is that, okay, like this sort of, the determination of this green shape, the law of large numbers, was given, I don't even remember by whom, but it's known for a while, perhaps like in the 1970s, 1980s, but Kurt Johansson looked at the fluctuations of the yellow around the green, of the blue around the green. That is, you look at the central limit theorem for the blue, and he proved that these fluctuations are also given by the same Tracy-Widom distribution. This was proven in 2000, so 2 years after the Tracy-Widom distribution emerged in the random permutation setup, right? So in this again is another example of a model, was a growth model in this case, whose fluctuations are given by the trace-width distribution. Starting in random matrix theory, moved to random permutations, and appeared in random growth models. Here's a bit of the story. It's interesting that actually the first time that random matrices were studied were in the works of Wishart on statistics. He was looking at sample covariance matrices, and over there, random matrices appeared for the first time back in the 1920s. Then it came the works by Dyson, some of which I roughly described at the beginning of the talk, which was the physicist who sort of brought random matrices to the spotlight in theoretical physics, and that was happening in the 50s, 70s. And at that stage, okay, from that moment on, the theory of random matrices started to grow on its own. There were several works in the 70s, 80s relating to dynamical systems, free probability. On a parallel line, at that stage, having nothing to do with random matrix theory, there appeared some works on stochastic PDEs, more in particular in the KPZ equation. When the KPZ equation appeared for the first time in the physics literature, let me stress, at this stage, we're having nothing to do with random matrix theory. And by the way, KPZ stands for Carter-Paris-Zhang, and Parisi is the same Parisi who just earned the Nobel Prize in Physics, also related to the work on KPZ equation. Right? Anyway, so at this stage, like things are separate. I'm just talking about on the top row there, like KPZ equations, the stochastic equation, on the bottom, random matrix theory, the development of random matrix theory. Right? And then in 93 came the work of Tracy Weed and also Peter Forrest, which I should honor, which computed for the first time the Tracy-Weed distribution in random matrix theory. In 98 came the work of Bagdad Johansson computing the Tracy-Weed distribution in random permutation problem, in the Ulan's problem. And in 2000 came the work of Kurt Johansson computing the Tracy-Weed distribution in the TASAP that I just showed to you. Right? Also, but like a great part due to those works of Bagdad Johansson, it started to emerge several works where people started to show up, they should start to obtain that the trace-width distribution describes fluctuations of quantities in a wide array of problems in mathematics, and then physics, and then engineering, and then statistics as well. Many names here, and I won't be able to go over all of them. But in particular, around 2012, it came a paper by Amir, Corwin, and Quastel, where they computed that the trace-width distribution also appears in the KPZ equation. Right? So it's one of those works which extended trace-width distribution to lots of other models, also to KPZ equation at that stage. And that's the next option I want to talk about, the KPZ equation. I'm not going to write it. Just want to say that it was introduced. It's a stochastic PDE introduced by Carter-Paris-Zhang in '86 in physics. It describes the evolution of a height function. So you have a certain height, I'm calling here h. This h depends on position and depends on time, evolves in time stochastically. So think about the blue curve that I showed to you in the traffic model, in the TASAP, which is also displayed here, right? So the blue curve here. So it was growing. So imagine that growth is governed by a stochastic PDE. In the TASAP is a discrete model, so it's not KPZ, but in the limit it becomes KPZ. So it's safe to say that this growth is sort of recovers the KPZ equation. As I said, so in 2012, but then the work appeared in physics in '86. Physicists liked it a lot, but there was lacking a good ground in mathematics to actually work with that. And in 2012, Amir, Corwin, and Quastel were able to compute, to solve the KPZ equation for a specific initial condition exactly. There was a formula there. I'm not going to go into the details, but basically what they computed was the one-point distribution of this KPZ equation. So you take the solution, the KPZ equation, this function, random function growing, and after a shift in time, you look at the one-point distribution, calling your h. What they computed is that, first they computed this one-point distribution explicitly in terms of what they call integral differential or different integral differential equation, in this case, integral differential Pauli-Wetzel equation, whatever that is. And also they compute that most important for us is that when time runs by, this one-point distribution converges to the trace-Widom distribution. In other words, KPZ is a time evolution determined by a certain distribution. And this distribution, when t goes to infinity, goes to trace-Widom distribution. So in a certain sense, the KPZ equation becomes the trace-Widom distribution when you wait long enough. And if the time goes to 0, you become a Gaussian. Also they compute there. Anyway, hand waving here a bit, but just to have in mind that even in the context of a stochastic PDE, this trace-Widom distribution appeared. Okay. Some keys ideas, very vague here, that what they do is that they discretize this KPZ equation and they prove convergence somehow relying on ideas that were already present in our proof here of the central limit theorem. Instead of looking at the KPZ equation itself, look at its moment generating function, or look at its Laplace transform, but actually here's a slightly different Laplace transform, is the Q Laplace transform. Okay, okie dokie. So far, we can sort of go over the things that we discussed in the sort of this pictorial way. So we start with largest eigenvalues of random matrices, and we saw that fluctuations of those converge to the trace-Widom distribution. And then we look at this problem of random permutations, and look at that. Random permutations, if you look at the correct statistics, the fluctuations of the longest increasing subsequence, those fluctuations also converge to trace-Widom distribution. We look at the TASAB, this traffic model, also trace-Widom distribution. And we look at the KPZ equation, also trace-Widom distribution. So why is that happening? I'm going to answer in a moment. But also, now moving towards the end, and also just to mention some results, things that we are investigating now, together with Promit Gusal from MIT, we actually found a nice connection, which was a connection directly between random matrices and the KPZ equation. So you can think about the KPZ equation as in the large time limit to go to trace-Widom distribution. So KPZ equation connects the random matrices in the large time limit. We were able to find a connection that holds true for every time. It's sort of a bit of a surprise, a nice surprise for us. So let me just go over that again with as few equations as possible and very quickly. Basically, what I want to go over with you is what we call a Q Laplace transform. So take some points at random. You could look at the Laplace transform of the moment generating function. Just want to look at its Q Laplace transform. It's this expression here. So we have here the random points appearing here, and Q is just a parameter here. Don't bother much. Actually, don't have even much time. But why? I mean, don't bother about the expression. But just let me tell you why we care about that. As I said, so the Q Laplace transform was used in the work of Amir Corin Pastel, and that was like quite a robust technique quite robust object to compute solutions to the KPZ equation. And actually, those ideas have been extended to a lot of discrete particle systems. Right? Tons of them, without going much in details. And here for us, we thought, okay, why not random matrices, right? If people do for discrete systems, why not a continuous system like random matrix theory? And it's somehow useful to detect like local behavior by tuning up the parameters that are in the Q Laplace transform, which basically boils down to this identity that I'm showing to you, but not going to explain with care. But basically, you can tune it up, and you can detect local statistics of random points by just tuning up this Q Laplace transformer property, right? For us, let me just, to state the result in more or less concrete terms, I'm just defining it again, but without, so this expression on the left is the one that appeared in the literature in discrete particle systems. For us, it's nice to sort of rescale it, but again, I don't want to bother much about the details. Let's just use it as is. It's just some different type of moment generating function, or what people say is the Q moment generating function, basically. There are some conditions here. Remember that before I talked about Gaussian matrices, but here we can assume a lot more. We work with what we call unitary invariant ensembles with one-cut regular potential. In particular, include those Gaussian matrices. Let's not care much about what that means, but I just want to stress that we are working with very general distributions of matrices here, right? There's a certain Q here, which is also a parameter, it's a function, sort of controls your statistics. Don't care much about it. Let me just say that we work with very general Q that are basically decreasing or go from plus infinity to minus infinity at the edge of the law of large numbers for the random matrices. Does not care much about the details, just want to say we're working under very general distributions and somehow general statistics as well that we consider for this Q Laplace transform. And what we prove is that this Q Laplace transform converges to the Q Laplace transform of the KPZ equation. That's the connection. There's also an underlying integral, an underlying point process for this Q Laplace transform, and actually also able to identify a new process that emerges. This new process is the determinantal point process, and the kernel of the determinantal point process is described by this integral differential Panevet-2 equation. Again, let's not focus on the details. Just want to say that the new process that emerged, and this process has interpretation in terms of the KPZ equation as well. Okay. Just to, and what I really want to stress that this is universal, as I said, in the distribution of M within a certain class and in the statistics Q as well. So regardless of those statistics and the matrix distribution, it still converge to the KPZ equation in the sense of Q Laplace transforms. So this is the picture, right? So we have that somehow what we're doing here, like a philosophical level, is that we're adding a time variable in the random matrix picture, and we are able to show that the random matrices connect to the KPZ equation, not only in the large time limit, but also for finite time. And these connections are there. And as I said, moving already towards the very end, I just want to say a few words why this picture holds true. So why do we have that many different particle systems go to the Tracy-Widom distribution? And this is what we call KPZ universality. And going very quickly, or better, let me just say in words because I'm running out of time. Basically, the story here is that those pictures that you see, so this diagram that you see here on the side are what we will call, we can see those as, let's say, a 1 point marginal slice of a bigger picture. What happened with this KPZ universality says that there should be some underlying structure on top of this picture. There should be an underlying process, two-dimensional process in this picture, so that when we start looking at marginals, time slice marginals of this underlying process, we should see all those different models in this picture. Even the construction of this central object was actually open for a while. It was constructed recently by Quastel, Matetsky, Quastel, and Remanick, and also by independently by Dalvergne, Ortman, and Virac, which is what we call the KPZ fixed point. So this is a very recent construction, and also saying in words, we also what I wanted to show to you, but I don't want to run over time, is that actually we also have results of similar flavor that we can describe this KPZ fixed point in terms of integral systems as well, connecting differential equations, which are somehow similar to those integral differential Panevet equations. But let me not go over there, and just so that I don't go over time, and just finish here with this picture, and thank all of you for coming here, and I hope I could at least entertain you for a little bit and give some flavor of what sort of objects appear in random matrix theory and also in random growth processes, right? How this Tracy-Widom distribution appears in the setup. Okay, thank you.
Thank you very much, Guilherme, for your talk. I first would like to open for, I don't remember exactly, Michel, do we clap in your show?
Usually
after the questions. Okay, it's not now. Okay, sorry. It's not time
Hold your hand.
Okay, so now we have time for questions. So, well, first of all, Guilherme, thank you very much for this incredible talk. It was very, very nice. I felt it was very nice. So, time for question, please. Michel, please.
Hi, Guilherme.
Hi, Michel.
Actually, my question, first of all, thank you for your presentation. It was a very cool presentation. I liked it a lot.
Thank you.
I need to warn that this definitely is not my piece of cake.
Of course.
But I just have one simple question. Maybe I misunderstood something, or maybe I just did not pay the attention that I
No
need
worries,
to
figure it
pay.
out.
But when you were talking about the eigenvalues, where you firstly talk about the convergence of this distribution, you show that the maximum eigenvalue converges to 2.
Yeah.
And right after you show that the distribution of the maximum converges to, I forgot the name of this distribution.
Trace Sweden.
Yes. And then you show the density and
Yes.
approximation.
Yeah, let me recover that.
Okay.
That for you. Let me just open here again and recover that for you. See, yeah.
Yes.
This one?
Yes,
Yeah.
exactly. Maybe you could show the comparison with the normal as well.
Yeah. Sure.
Yes, perfect. So I can see that first, the maximum is not around 2, but less 2. Is it
between 3 and 2, right?
Between, no.
Yeah, or -2. Sorry, -3 and -2.
Yes, it's around -2. Is this just a problem of signal or something?
I mean, the expression for the maximum is transcendental. So there's no like easy expression for this maximum. There's no parameter here. The trace radius distribution, this one doesn't have any parameter, right? And the maximum is not the mean. Different from the Gaussian, right? Because in the Gaussian, you have that the maximum is the mean. Right? But here it's not true. Right? It's not centered around so it's really, it has a little bit, it's a little bit skewed here.
But should this mass of probability be, should it not be around 2 or close to 2 or something like that, since it's converging to 2?
No. Wait. So just be careful, because the eigenvalue is converging to 2, the maximum eigenvalue, but I'm not looking exact the distribution of the maximum eigenvalue, but I'm looking at the fluctuations. So I'm really making like a new centering, right? So really, I'm talking about here, if you look at this t over n2/3. So I'm doing a zoom here.
Okay.
So I'm really like looking at how my eigenvalues are close to this 2, and now I'm zooming. At the same time that I'm blowing up the size of my matrix, I'm also zooming in. So I don't see anymore like the 2 itself, but I'm sort of rescaling everything there. So the picture that the way you should look at this picture is that, for instance, here, it's very likely that, for instance, I am around minus. So here I'm saying the distribution tells me that I'm very likely to be close to -2. So what if I translate to the picture of the eigenvalues, it just means that it's very likely that I am -2 over n2/3, right?
Okay, I got it.
Yeah, there's this little skew there. And then from this picture, you already see that it's more likely to find eigenvalues to the left of 2 than to the right of 2. Why? Because to the right of 2 would mean that I am looking here at the tail, the very right tail of the Tracy-Williams distribution, right? At positive values, but there the Tracy-Williams distribution is very low.
Okay. Okay, thank you, Guilherme.
Thank you, Michel. Victor?
Good afternoon, Guilherme. Thank you for the talk. Oh, I found it so much impressive, all the relations with this distribution. I have 2 questions.
Yeah, please.
The first one is if it's known any result regarding law of larger numbers or central limit theorems for random permutations with other distributions of the than uniform?
Oh, yes. Actually, that's a very interesting question, because actually that's basically, let me go, let me just see here now, share again. Let me go direct to this slide. Here, let me share again. Let me share already my whole screen, because then you can see my mouse as well. So I'll share my whole screen here. So you remember this picture here?
Right.
So for, I don't remember in the original work of Blake-Johansen if they consider already more general distributions of random permutations, but the answer to your question is basically what led to lots of things here between the 2000s and 2010s. So people started to develop techniques and coming especially from representation theory, but not only, to get like natural distributions on random permutations and in other objects as well, which are not necessarily uniform, but are supernatural from the point of view of representation theory. All those different distributions have connections with concrete models, like TSAT, for instance, and other versions. And yes, there are connections with trace-Whedon distribution there, and also with other quantities as well. So yes, so there are lots of literature here, which also go through to recent days. Absolutely. Yeah. And even there's a student of mine who's studying that for his master thesis. Yeah, he was here a little earlier. If he's here, he's going to recognize that perhaps. Absolutely, Victor.
Cool. Thank you. The second one is you mentioned in 1993 Tracy-Whedon first. Can you recall what you talked about?
Oh yeah, Tracy-Whedon just mean here the official proof that largest eigenvalue of random matrices converge to the Tracy-Whedon distribution. So that's why the distribution is called Tracy-Whedon, named after Tracy-Whedon. But actually, Peter Forster computed the limit, that there was a limiting distribution, and he computed this limiting distribution of the fluctuations of eigenvalues of GUE matrices. So they started with a GUE matrix, computed fluctuations of the eigenvalues of GUE matrices. Peter Forster computed this limiting distribution in a certain way, but Tracy-Whedon were the ones who also computed independently, but they went one step further, and they characterized it in terms of or in terms of ordinary differential equation, in terms of Plain-Levé equation. So the formula for Tracy-Whedon for Peter Forster was a Fredholm determinant, but Tracy-Whedon were the ones that got it also in the form that's most known, which is like in terms of solutions to Plain-Levé equation. Right, so
this was my second question. So yeah. This distribution was discovered in this context?
In random matrix theory, yes. In random matrix theory, yes.
Cool, nice.
And it took until 98 to be found elsewhere in the case for random permutations. Yes.
Okay, thank you so much.
My pleasure.
Okay, thank you, Victor. Any other question? Well, I have some observations and questions. First, I observed that you said that the first to consider random matrices was a statistician, but you decided not to present this to us. We are statisticians. I hope when you speak to physicists that you just say that, okay, it was invented by statisticians.
Yes, I will. And actually, to be honest, I was afraid of doing that. I wanted to. I added a slide for that, and I removed it from the last minute, just because I was entering into a dangerous territory. Because when you talk to someone, you don't know the subject, and the other person doesn't know as well. You can pretend, but you don't know. The other people do know.
Yeah.
We had a basic sample covariance matrix. If you look at the expression, you see immediately, like, you start trying to, you have a random vector of Gaussians, and then you have several samples, and then you look at the matrix that corresponds to those samples, and you try to do how to say? You see why I didn't say, because I don't remember the names. But you try to do basically you try to estimate the covariance between those vectors, and when you assume that your samples are Gaussian, if you assume that they are Gaussian distributed, this covariance matrix that you're trying to estimate, what they call sample covariance matrix, is precisely the Gaussian matrix. In that case, orthogonal, not unitary. Oh, sorry, in that case, symmetric, not Hermitian. Anyway, the real version of it.
Okay, no, I was just calling the attention. It was funny because we have also had a guy from physics who came here, and he said that he would speak on the physics part to us, and if he was speaking the same talk to guys from physics, he would speak about the statistical parts of the paper. So just to be sure that nobody will really completely understand what we
and no one will call them mistakes, right?
Exactly. Okay, but okay. So my first question would be concerning your the last slide you present. Just a curiosity, because you seem to say that so we have so much things, we are all pointing through to the tracing window distribution, and you're saying that people are trying to find some universality among everything, but yes, you were able to make a link between two small squares here. Do you know where does it mean that this picture, does it mean that the other links have not been, there are no other link, for instance, between random permutation and largest eigenvalue random matrices? Are there some paper trying to linking that? Or
oh, yes,
no?
Absolutely.
Okay, okay.
And that has a lot to do, for instance, with the question that Vitor asked me about concerning other possible distributions of random permutations. Okay. So you can construct actually. So those things here, for instance, Tay-Sep random permutations, Johansson's result, if I remember correctly, was about Tay-Sep, which came like 2 years after random permutations. The point is that you can connect both. Okay. For instance, right? And what happens is that people use those tools from representation theory, and they describe some discrete growth processes. And when you start looking at marginals of those processes, you start recovering Tay-Sep or start recovering random permutations or start recovering other things. And I have other slides here that I could show to you, for instance.
It's beginning to be complicated.
Yeah. So just want to show the other links here, for instance, which are those, right? So you start looking at marginals, you recover those at the discrete level. And the point is that now people are starting to be able to do that at the continuous level as well. At the discrete level, it started with random permutations, not necessarily uniformly distributed. And you could describe discrete growth models whose marginals were reduced to the models that we knew. But at the level of those discrete objects, this big object, but still discrete, people could do still calculations. But now they are also able to strike the continuous limit of those models upstairs, and those continuous limits, they converge to the KPZ fixed point. And then you can also make slices of those KPZ fixed point and try to look at continuous processes over there. And basically there are lots of arrays pointing towards several objects there. Absolutely.
Okay. Okay. So, okay, my technical question perhaps would be about the literature. Are there some papers trying to estimate for instance, when you have a result where you say, for instance, for the permutations, can you come back to the statement for the random permutations? Yeah. When you have like square root of n and a 2, I don't remember exactly what was the limit.
Yes, I guess. Let me go back to the result. It's coming there.
It's slowly coming.
Yeah.
Yeah. Okay. So here, for this central limit theorem, then next there is one. Are there some results trying to estimate the probability that you deviate from the mean? In this case, so
you mean trying to compute large deviations?
Exactly, large deviation or the concentration inequalities. Yeah.
Yes.
Which are large deviation, but at fixed n, for any n, not in the limit. Yeah.
Yes.
Okay.
There are.
Okay. So
not
everything has been done.
Okay. A lot has been done, but a lot is open.
Okay.
I'm not very familiar with the literature to tell you exactly what's open, what is not. But there are absolutely lots.
Okay.
I know, for instance, that because I was doing some large deviations for 6-vertex model. and it's a very classical model. Apparently, it has not been known.
Okay.
But that's how actually it's a funny story. That's how we got those Laplace transforms from random matrices, because we're trying to do large deviations for instance, stochastic 6-vertex model that contains the ASAP, for instance. Okay. So that's how I got to those Laplace transforms. Anyway, but yes, I'm not 100% familiar with that. Certainly, I know whom to ask. For instance, this collaborator of mine from it is more familiar with that. But I know also that there's, although lots is known, there is also lots to be known. We first get normally the fluctuations, and then like large deviations or tails or whatnot come like behind it, but not immediately sometimes. Yeah.
Okay. No, thank you. Very nice. Are there any further questions?
Could you talk about something about the relation between last parsec percolation, something that I like, percolation, and the KPZ equation that you pointed out in a slide?
Okay, I don't want to hold people here for a long time, so let me try to be as brief as possible.
Well, otherwise you can also, you can also have, no problem. If you are able to answer very fast, I would say, like some words, but you can then next continue on in the room, okay? Just...
Yeah, sure. Yeah, so the quick answer, there is the quick answer is, I talked about this, let me see here. I talked about this model, DaySap, right? If you rotate this DaySap, so you're asking me about the last passage percolation or last passage percolation? Right? Yeah. So if you look at this height function and you rotate it appropriately and you look at that carefully, you're gonna see last passage percolation there. And so there's one side of the picture. The other side is that you can place here another variable, which is sort of here. I'm just allowing jumps to go to the right, but I could allow jumps to a chance to go to the left, right? And if I go to the right or to the left, if I allow them to jump both to the right or to the left with the same probability, this is a symmetric exclusion process, right? But then I do it what they call weakly asymmetric exclusion process. Weakly asymmetric means that I'm almost symmetric, but my chance of jumping to the left is just a tiny bit smaller than the chance of jumping to the right. And then I do that, this tiny bit, I scale that tiny bit according to the number of particles. And I let the time run, and the number of particles grow. If I do that, this is like what they call the weakly asymmetric regime. And when you do that, you converge the KPZ equation. So you look at your corresponding height function, the height function converges to the height function of the KPZ equation. So there are other connections, but basically this, I would say that this stage, the easiest to do. First, you go from last passage percolation to ASAP actually, and then from ASAP you go to KPZ. You go to KPZ through the height function.
Okay, that's so much interesting. Could you give any reference about that?
There's a book by Bike, Deft, and okay, I don't remember now the third author. This is like from 2016. That's a good starting point. But just write to me and I'll give you more references.
Okay, no problem. Sure. Yeah. Thank you.
Okay, thank you for, I think we should conclude with these questions. Thank you very much, Guilherme. I think now it's time to clap hands because, he deserves this. He answers so much questions also. So thank you very much.